and I'm going to record you guys. All right. So the first thing I kind of want to think through here is, what do we know about samples? Samples aren't perfect, but they are all we have. Is everybody with me? So the big difference between everything that we did in Unit 6 is the variable that we were doing inferences about was a categorical variable, okay? So for example, if I remember the free response question about the environment statement versus the economy statement, and like when you guys think through, could you find the mean response to that question? I'm just going to do economy plus environment plus environment plus environment plus economy and divide by 6. Does that make sense? You can't find a mean of a categorical variable. So for categorical variables, we use p hat to estimate p. For quantitative variables, where everybody's answer is a number, we use x bar to estimate mu. So we're switching from using p hat to using x bar to conclude about mu. Now, with quantitative variables comes another calculation besides just the mean, okay? We also have the standard deviation. So you guys, we've heard that word once or twice, yeah? Okay. And so what we're going to need to do is we're going to need to use S in place of sigma, where S is the standard deviation of my sample and sigma is the standard deviation of my population. Now, it is a much bigger deal to use S in place of sigma than it was to use p hat in place of p. We'll get, today's really talking about the why of that, but we're going to talk about that a lot. Everybody good? All right. So, overall, all confidence intervals are a statistic, and then my margin of error is made up of a critical value times the standard deviation of a statistic. So which statistic would I use to estimate a population mean? X bar. Plus or minus, and I'm just going to use a critical value. And instead of using the square root of p hat 1 minus p hat over n, we don't want to use that one, because what do we know about x bars? They have a completely different formula for their standard deviation. Everybody good? Sigma over the square root of n. What else was like when we start thinking through the distribution of all those x bars? There's one other thing we kind of think through. If this x bar and this x bar and this x bar, if I take a whole bunch of x bars, right? Let's go through the 3 things we would need to know. What's the shape? When? When were the x bars normal? You guys, NP, N1 minus P greater than 10 doesn't make sense when you don't have a P. What was the other way we checked for normality? It can't be any version of NP and N1 minus P.
Both samples.
We're doing a 1 sample procedure right now, okay? So this will be normal if the population is normal. What if the population isn't normal? No, then you can't do it. The x bars will still be normal if, this is a huge if if my sample size is large enough, then it doesn't matter because, like, let's say I have this super skewed distribution. If I take a large sample, every single one of those samples will be skewed. But the means of those samples would all be about the same. The means would be normal. Okay? So how large was large enough? 30. Cool. That's I just think that's going to come back in a few minutes, okay? All right. So a one sample Z interval means our critical value will be a Z star, no different than the Z star you've always used, times the population standard deviation divided by the square root of n. Okay. Now, how do you calculate standard deviation?
Average distance from the mean.
It's the average distance from the mean. So guys, and then what's the goal of the confidence interval? To estimate the population mean. So, you guys, if I don't know the population mean, can I calculate the population standard deviation? That doesn't make sense. I would need to know the population mean to be able to calculate the population standard deviation. Okay? So we don't actually use Z intervals for mu. However, there's one way I could ask you about this. And that is to find sample size. And then they're going to make up what they think the population standard deviation is. But I want you guys to understand that that's actually really stupid. Okay? It's not actually possible to know the population standard deviation without knowing the population mean. But they're going to tell you, hey, I know my population standard deviation is 5. And it's important that you guys start making distinctions between population versus sample. It hasn't been more important till now, but it's going to start getting really. So that 5 is describing the standard deviation of the entire population. All right, and so if I want to find a 95% confidence interval, and I want my margin of error to be within 1.2, I want to do my Z star times sigma over the square root of n. That's my margin of error. Because that's the part that comes after the plus or minus. Now, do I know what Z star is? 1.96. Do I know what sigma is? 5. What are you guys doing first? Divided by 1.96? Cool. Then what? So this looks a little bit different than the previous ones, right? What should I do next? Move that n to the other side by multiplying it. Cool. And I think you get something like 8.16 has to be less than the square root of n. Give or take. Yeah? Then? So your sample size has to be bigger than 67 monkeys. I don't know why, but I feel like I don't know why, but something about having the answer being 67 monkeys makes me giggle. Am I the only one that finds that like just a funny answer? I think it's kind of funny. 67 monkeys. What do you guys think so far? All right. Now, before rolling on, I want to bring up again, we need to use S in place of sigma most of the time. Because we like this part, okay? We don't know the population standard deviation in actual practice. So what we do is we use x bar plus or minus, and goes the square root of n, and we put an S on the place on top here. So we have to use the sample value, okay? And when we do that, using S in place of sigma on this formula is way bigger deal than using p hat in place of p on this one, okay? Because S is not a good estimator of sigma. And let me give you a really good example, okay? All right, now, I want you guys to think about the standard deviation of heights of people in this building. Then I'm going to take a random sample of 3 people. Is everybody with me? And this whole time, I want you to think about the standard deviation, how much variability there is in the heights. And the sample I'm going to take is going to consist of myself and Ellie and Chloe. Talk to me about that standard deviation.
It's really small.
Really small, because you're what, 5'1"?
Yeah.
You're what, 5'1"? I'm what, 5'1"? On a good day. Okay? You guys get what I'm saying here? And just as silly though, so are you guys with me that the standard deviation of that sample is probably smaller than the standard deviation of the population? Okay. What if I took a random sample of 3 people, and those people include Ryan, myself, and Daria? Daria would probably be close to the mean, I would think, right? And the distance from that mean is only 2 big points. Do you guys get what I'm saying there? Mm-hmm. That's probably larger than the population standard deviation. Do you guys see how S can be a crappy estimator of sigma? Okay, one more question. What if I took a sample of 100 people? Would S still be a crappy estimator of sigma? Not nearly as crappy, right? Does that make sense? Okay, so as we go through this, we're going to use a different kind of critical value that puts more wiggle room in because S is a crappy estimator of sigma, and the name of that critical value is T star. So we're switching from Z intervals to T intervals. And to be honest, just about everything with a mean will really be used as a T interval. So the formula for a one sample T interval for mu is in fact that x bar plus or minus T star times S over the square root of n. Okay? And essentially what these T's do is they give extra wiggle room based on the fact that we're using a not so good estimator. That we're using a value in our formula that we know isn't great. Okay? So we choose T because S is a meh estimator of sigma. P hat is an awesome estimator of P. S is a estimator of sigma. All right. So, to find Z star, we used that standard normal curve where the mean was 0 and the standard deviation was 1. And that was the distribution of Z scores. So basically, they figured out, a long time ago, stats dude figured out that the distribution of T's, the way they calculate T using S instead of sigma, is really, really close, but has a little bit more variability. It's more spread out, so the peak doesn't get as tall, okay? And just like when I said my sample size was 3, meant S is a really bad estimator of sigma, but my sample size of 100 isn't, okay? The spread of a T graph is very much related to the sample size, okay? So T distributions, like there's only one Z distribution. There's many, many, many T distributions. They're all mound-shaped. They're all centered at 0, okay? And we don't describe them with their standard deviation. Instead, we describe them with what we call degrees of freedom. But the degrees of freedom is really just, it's not n equals 1. The way you calculate the degrees of freedom for any given sample is you take the sample size minus 1. There is a reason behind that. I promise you, you don't want me to explain it to you. Okay, so real quick, y'all. Let's go through calculating some of these T stars. All right, so the first thing you're always going to do is draw a graph. The center of that graph is going to be 0, and instead of labeling the standard deviation, what you're going to do is label the degrees of freedom. So what are my degrees of freedom if I'm telling you I want to do this for a sample size of 30? 29. All right, before we did 95% confidence, we just found that middle 95%, right? And then I said, well, what's this tail? 2.5%, which I'm going to write as 0.025. Now, how did we actually figure out what the boundary is? Inverse norm. Can I use inverse norm? No, because I don't know the standard deviation. However, go ahead and pretend to use inverse norm real quick. At least do that first step of hitting second vars. See anything that might help? Pick inverse T instead. Now you notice that it asks you for the area. It doesn't give you that left, center, right option anymore. So you have to give it the left-hand area. Okay, center won't be an option anymore. But you should get like negative 2.04.
What do you mean by the left-hand area? Do you just mean 0.025?
But that T star is not positive or negative. It's both and neither. So it's going to be plus, it's really just T star equals 2.04. You're going to ignore the negative. What do you guys think so far? Is this bad? Is finding T star bad? Cool. How would that change? Before we actually do this next one, if I go with this larger sample size, S is becoming a better estimator of sigma, what should happen to my critical value? It should go down. More important, in reality, instead of saying going down, what if we said it's going to get closer and closer to 1.96? Okay, so my degrees of freedom shifts to 49. But other than that, it's the same picture. My left-hand area is 0.025, so that's the one I'm going to put to the calculator. And I think we end up with like a 2.01.
You just all extend the T-star as positive.
Mm-hmm. Well, in reality, so this is negative 2.01. This is positive 2.01. In reality, T-star is both of them. It's plus or minus. But like when you think about how do we use that T-star, it follows a plus or minus. So like that really the plus or minus of T-star is that the plus or minus in the margin of error. Okay, why don't you guys find these last two? Is it 2.68 for the second one?
Yeah.
How are you guys feeling about finding T-star? Good?
Why is T-star higher for the fourth one?
Because it's way more confident. Think about to go from the middle 90% to the middle 99%, you would have to widen that out.
So then what's the Z-star number for 99%?
2.33.
So it is closer.
Farther.
Makes sense.
Yeah. Everybody okay? All right. Now, hey guys, I got great news. I think you'll do a good job remembering what the three conditions for a one sample T interval are. Do you guys think you can remember these? Cool. And two of them are done the exact same way. We're going to look for, is the random condition, are you given that it was a random sample? And for independence, we're going to say our sample size is less than 10% of our population. Now, you guys, if I give you a list of numbers, can you tell me what P, NP, and 1 minus P are?
Oh.
You don't have a percent of what? You don't have a P. If your data is just a bunch of numbers, what you have are the mean and the standard deviation and the sample size. You with me? Okay, so the whole normal condition is based off of those X bars being normal. When were the X bars normal again? If my sample was big enough. That was one of them. So if my sample size is 30 or more, all I have to do is state that the sample size is 30 or more and I'm done. Okay? Now, if the sample size is not 30 or more, we run into another issue. Okay? So the X bars will be normal if either my sample size is big or if my population is normal, okay? So now, are we going to know anything about our population? We're not going to know the shape of the population, okay? So instead, that's an arrow. What we're going to do is say a graph of the sample suggests we can assume normality. Now, what does that graph need to look like? That answer is, it kind of depends, okay? So we kind of break our sample sizes into 3 groups. Really small, medium small, and, big enough. So if my sample size is bigger than 30, I don't need to worry about the graph at all, okay? If my sample size is really small, and we typically use 15 as that cutoff, okay? Then we need our sample to be close to normal, okay? If it's like between 15 and 30, we just need our sample to not have any skewness or outliers. It doesn't have to be perfectly normal. It doesn't even have to be mound-shaped. Like if it's a symmetric distribution, it's fine. Just no major skewness or outliers, okay? All right, so let's do one. Now, I see construct and interpret. That makes me want to draw my boxes. And so this is essentially the tension on screens. I don't really understand what screen tension is, but I'm assuming it's something that's important. Okay? So what do? What goes in the first box? Procedure and conditions. And my procedure should be A1 sample, T interval, for mu. And guys, what's mu? It's what? The true mean screen tension. Cool. All right, we've done our procedure well. Next is conditions. What's the first one? And is the random condition met? We're given it's a random sample. Cool. All right, normal. Is the normal condition met? We don't know. We have some more work to do. Certainly the sample size version is not met. But the other one, what we do, so the next thing we need to do is come up with a quick graph of the sample. In my opinion, the quickest, easiest graph to do of the sample would be a quick dot plot. So I'm going to look at these. It looks to me like the highest one is 343. The lowest one's 234. So I'm going to make this one 230, and then I'm going to count by 20s. If you did a different interval, it would be fine. As a math teacher, I'm pretty good at making sense of whichever ones you guys do. And then we're just going to make a dot for each one of these different screen tensions. Does that look mostly concentrated in the middle? Yeah, so I'm going to call it mostly mound-shaped, which is great. That's what we want. So do you think it's reasonable to assume this came from a normal population? Like if the sample, it looks like it came from a normal population, right?
I'd be hesitant to say that.
Would you?
Yeah.
I wouldn't. There's only, think of it this way. Don't fixate on the fact that 270 was there twice. If one of those 270s had been a 271, it would be like, this looks like there's a mound a little bit on the left because there's two 270s. But in reality, they're pretty darn. I still see a little bit. Do you see what I'm saying?
Yeah, but how does that look normal to you?
So imagine if I made a histogram of this. Okay, I'm going to make that histogram in red so that it stands out, okay? It might look like this. That's what that histogram would look like. And when I look at it that way, that looks close enough. Because it's never going to be perfect, right? It just needs to be approximate. And what you should really see, I'm going to get rid of the histogram because it's seeing that these concentrations towards the middle, that's what makes me see normality. Okay? Next condition, independent. Hopefully 14 is less than 10% of these screens, of screens from this manufacturer. Yeah.
Do we have to say anything for the normality other than drawing a graph?
Because I said it was mostly mound-shaped, like describing what you're seeing. But yes, you absolutely need to say, what did you look for in the graph? All right, for this next part, I'm going to be very, very kind to you guys. Now, do we have any summary statistics or anything here? No, we just have the raw data, yes? Okay, so it turns out that if you're given the raw data, what you need to do is put it in your calculator and you can run the test from the data in your calculator. I'm not going to make you guys type these in. I have it in mine, and if you guys are comfortable, we can just use mine to get there so that you guys we don't have to take the time to type it in. Okay, so your rule of thumb is going to be, at any point, if you have to tell a value to the calculator, you need to communicate that value to me. Or if the calculator tells you a value, you need to communicate that value to me. That's your rule of thumb, okay? So we're going to go to stat. We're going to arrow over to tests. And guys, as I do this, tell me when you see something that might help me do a one sample t interval. How about number 8 that says t interval? So you're going to pick the t interval. Now, if I give you the summary statistics, like in my blurb I say, I took a random sample of 50 people, I found that the mean and standard deviation of that sample was blah, blah, blah. Then you're going to highlight the word stats here, and the minute I go over to that, all of a sudden I have a space where I can put in the mean and the standard deviation stuff. That being said, do I have the summary stats? No, what I have is the raw data. I have that raw data stored into my L1. So I'm going to go back to stats, and if I hit L1, it's there. I have the 90% confidence level there. I hit calculate, and you'll see it gives me the mean. The mean was 290.5. The standard deviation was 30.1. The sample size was 14. Now, how else could you have found that? You could have found all of those things by putting them in your calculator and doing the one variable stats. All right. Then what's my interval? 276.27 to 304.73. You are, again, always allowed to use the calculator shortcuts from here on out. And I just got that from looking on my calculator screen. Only one more thing to do. So I'm going to interpret this with, we are 90% confident. So far, does that feel terrible? That the interval from 276.27 to 304.73 contains the true mean screen tension. So when you think about this interval, the interpretation's still the same thing, right? It's just like this is essentially going to be whatever mu is instead of whatever p was.